Hi everyone. So this is lesson 2 on the travelling salesperson. Hopefully you've watched the video about bees and seen how clever they are. And we're gonna carry on and learn about the travelling salesperson. So last lesson, we found out that you have an upper bound and a lower bound. And the optimal solution lies between those two things. So we can't solve the traveling salesperson algorithm exactly, but we can find a best upper bound and a best lower bound and sort of narrow the gap and know whether we've got an optimal solution between those two things. So today we're going to think about finding an upper bound. Now, finding an upper bound just uses algorithms that you already know. So you need to find a minimum spanning tree. And to do that, you can use Prim's algorithm or Kruskal's algorithm. So you find the minimum spanning tree, then you double it, and then we just look for shortcuts by hand. So we'll go through one of these, and then I'll just give you a couple of questions to do at home. So I'm going to use Kruskal's algorithm today. The question will either suggest which algorithm they want you to use. They probably will suggest which one they want you to do because they want you to all do the same. But remember that the minimum spanning tree that you get from either algorithm is the same, so it doesn't really matter. So if I start by using Kruskal's, the shortest arc is that one there, so CD, and then ED, which is 3, and then FE, which is 5, and then AF, which is 6, and then BF, which is 7. Oh no, CE. Back there, I just automatically ignored that one because it would have created a loop. Sorry, I should have said that. So, yeah, BF, which is 7. Okay, so there's my minimum spanning tree. All right. And that's got a total weight of 23. Okay. So this obviously allows our travelling salesperson to get to every one of the vertices, but because they are going to have to kind of go out to work, visit everywhere, and then go home, we would need to double all of the lengths because the most simple way they could do that is they'd sort of go up there, back, up there, up there, up there, back, back, back. So they're going to kind of cover every route twice. Okay, so if we double the minimum spanning tree weight, it gives us an initial upper bound of 46. Okay. Now I find it really, really helpful to draw the doubles on there. All the things I'm doubling. Okay. So that's our kind of really, really sort of straightforward initial upper bound. And up to here, it's really easy to program into a computer. So Prim's and Kruskal's algorithms are really easy to program into a computer. Doubling it is obviously easy to program into a computer. Now, the next part of finding our upper bound is hard to program into a computer because it's done by inspection and it's looking for shortcuts. So here, this actually looks a little bit complicated. So I'm going to draw it out in a slightly more simple way. I'll pause the video while I do that a second. Okay, so that's just got all of the kind of extra arcs taken out of it, so it looks a little bit more straightforward. Now, we're going to, the next part of finding the upper bound is improving it, so looking for shortcuts. So in the question, they'll kind of guide you with how long you should spend doing this, because it's an exhaustive process. So it could take you ages and ages and ages. And the exam board don't want you wasting loads of time in the exam. So they will guide you along the way. Just sort of have a go, see how many you get in a few minutes, and hopefully it will improve. Right, so where could we go? So the one that's jumping out is this one here that we haven't used, this AD to me. So AD would go obviously there, and it would, that's got a weight of 12, and AF is 6, EF is 5, and DE is 3. So these ones add up to 14, and 12 is obviously less than 14. So that would be an improvement. That would be one option. Okay, so AD 12 is less than 14. I'll just write that there so I remember. Another one that I could use. Okay, so this one here kind of avoids going all the way around there, so that looks like quite a good option. So BC would go there, and that would be 9. So BF 7, FE 5, 3, 2. So they add up to 17. So that's much, much less. Okay, so actually that one, I'm not interested in that one, because this one improves it. I can't make both improvements because then these ones here wouldn't be linked together, and it wouldn't be a minimum spanning tree. So you have to be careful not to miss vertices out by making too many improvements. Are there any others? That one there, I can see that that one there isn't going to improve anything. And that one there isn't either. So I think because 14 is greater than 13, which is the bit that it would cut off. So I think, doing a quick inspection, I think that that is my best bet. Okay, so I would be using, I'll use a different colour. I'd be using this one here. And I won't be using that one, that one, that one, or that one. Okay. Great. So my new possible route could be A, F, B, C, D, E, F, A. And my initial upper bound was 46. And we're not using that 17 anymore, but we've changed it to a 9. So the new weight of that is 38. So that is called my improved upper bound. Okay. So it might be that I've missed something, but I've made a good improvement. In the question, it might say, make an improvement to give you an improved upper bound of 38 or something so that you know you've got it right. It might say, reduce the weight of it by 8, or something like that. So they will give you some guidance about whether you're getting it right. So that is how to find the upper bound. So now we know that our optimal solution is less than 38. It might be 38. It's very unlikely to be 38, but it might be. And next lesson, we'll look at finding a lower bound and then finding our optimal solution in there.